Hi fourth year, welcome to Unit 3, Chemistry and Society. We are going to kick off today with Lesson 1, Reactivity of Metals. So we've already looked at metals before. From Unit 1, you should remember that metallic bonding is the force of attraction between positively charged ions and delocalized outer electrons. We should also remember that metals are able to conduct as solids or liquids because these delocalized outer electrons are able to move. So the outer electrons, the electrons furthest away from the nucleus in a metal, are what's called delocalized. They're free to move around the whole metal structure, they're not tied down to one atom. And this is what allows metals to conduct electricity when they are solid. So, the outer electrons in a metal, which is these buddies here in red, are free to leave the metal atoms. And when they leave the metal atoms, those metal atoms become positive ions, seen here in blue. These outer electrons, once free to leave, flow around the resulting ions and they are called delocalized. On a larger scale, we have delocalized outer electrons, we have positively charged ions, which consist of positively charged nuclei and inner electrons, so all the electrons that were not in the last shell, the shell furthest away from the nucleus. Those electrons are now delocalized. So a metal then can be considered to be a regular array of positively charged ions in a sea of delocalized electrons. We like to call the delocalized electrons a sea because they flow around and through the positive ions, and that flow is what allows the metal to conduct electricity. So, each positively charged ion isn't just attracted to one single delocalized electron, it's attracted to a pool of them. And each electron is attracted to the positively charged ion. These electrostatic attractions hold the whole metal structure together. So an electrostatic attraction, for those of us who don't remember, is an attraction between something which is positively charged, in this case our positively charged metal ion, and something that is negatively charged, in this case our negatively charged delocalized electrons. So electrostatic attractions are attractions between something which is positively charged and something which is negatively charged, and it's this attraction that holds the entire structure together. The delocalized electrons, as I said before, are not attached to any ion in particular, and they are free to move throughout the metal lattice from end to end, side to side, in any direction that they fancy. So, metals can conduct as solids and liquids because these delocalized electrons can move. In order for a substance to be able to conduct electricity, it needs to have freely moving charged particles. In a metal, our freely moving charged particles are the delocalized electrons. So we have metals that react with oxygen to form metal oxides. We have metals that react with water to form metal hydroxides and hydrogen. And we have metals that react with dilute acid to form salts and hydrogen. Now, some metals will react with acid, water and oxygen. Some metals will react with water and oxygen. Some metals will only react with oxygen. And these reactions give an indication of how reactive the metal is and allow us to be able to put metals in order of reactivity. The order of reactivity of metals is based upon reactions with water, oxygen and acid, and is given by the Reactivity Series, or sometimes called the Electrochemical Series, which is found on page 10 of your data booklet. So page 10 of the data booklet has this list here, and as we go from top to bottom, our metals get less reactive. So we have our most reactive at the top, least reactive at the bottom. Now some of our more eagle-eyed pupils among us will have spotted that we have hydrogen here in the middle. Now hydrogen is a non-metal and is there for comparison. So there to allow us to compare how reactive these metals are compared to how reactive hydrogen is. So, reactivity of metals continued. This is what you need to know. The general word equations for reactions with water, oxygen and acid. So metal plus water gives metal hydroxide plus hydrogen. Need to know it. Metal plus oxygen, metal oxide. Need to know it. Metal, acid, salt plus hydrogen. You guessed it, you need to know it. So these three equations shown in yellow, you must know these. They're important. So when a metal reacts with water, you form a metal hydroxide and hydrogen. When metal reacts with oxygen, you produce a metal oxide. And when a metal reacts with acid, you get a salt and hydrogen. So let's look at reactions of metals with oxygen. Most metals will react with oxygen to form a metal oxide. Some of them, like sodium, potassium, lithium, calcium, will burn with really intense coloured flames. Some metals like iron will glow when they're heated in oxygen. And for some, colour change is the only sign that a reaction has occurred, and examples of those types of metals would be copper, lead and mercury. My second years found it really interesting that the Statue of Liberty in New York, which to most people appears like a greeny blue colour, it was originally made of copper, so it was a coppery colour, and over years of reacting with oxygen in the air, it turned green. So that is a very visible example of a colour change representing that the metal has reacted with oxygen. Of course, you have some metals that don't react at all, so metals like gold, incredibly unreactive, will not react whatsoever. So now that we've covered the kind of different rates at which metals can react with oxygen, you must also be able to write balanced ionic equations for reactions of metals. Now it gives us an example here, and it says copper reacts with oxygen to form copper 2 oxide. Now before we jump straight into a balanced ionic equation, we first want to get a balanced formula equation. So the balanced equations that you've done before, we want to write one of those for this reaction. So what we have is we have copper, which is Cu, reacting with oxygen, so plus oxygen gives copper oxide. Now, I know this formula off the top of my head. If you did not, you would use S, V, S, D, F to work it out. So our symbol for copper is Cu, our symbol for oxygen is O. The valency of copper from the Roman numerals is 2. The valency of oxygen, as it belongs in group 6 of the periodic table, is also 2. If we swap those over, 2, 2, divide down 1 to 1, our formula is CuO. So I'll pop that in here just now, out of the way. So here is our equation. Copper plus oxygen gives copper oxide. So, is this balanced? No. We have copper, oxygen, we have 1, we have 2. On this side we've got copper, oxygen, 1, and 1. So my coppers are balanced, but my oxygen is not. I have 2 on this side, I want 2 on this side here. So I'm going to pop a 2 down in front, which means I have the 2 oxygen that I need. But now my copper is unbalanced. I have 2 on this side, but only 1 here. So what I will do is I will pop a 2 down here. Balanced. Now, we now have our balanced equation. What we are going to do now is we are going, once this is rubbed out, very time consuming. Okay, so we now have our balanced equation. We are now going to add in our ions. And by add in our ions, I mean we are going to identify our ionic compounds and we are going to insert the ions for those. Now, quick reminder, our ionic compounds are those made from metal and non-metal ions. So, copper is just metal, not ionic. Oxygen, non-metal, not ionic. Copper oxide, on the other hand, is made from copper ions and oxygen ions. So it would, in fact, be an ionic compound. So here is how we write that out. We have 2 copper plus O2. So the first part doesn't change. It's the second part that does. So the 2 remains in place and I'm going to bring in brackets. Cu2 plus. The charge on the copper ion is the same as its valency. Because it's a metal, it would be a positive ion. Our oxygen has a 2 minus charge. And that is your full balanced ionic equation for the reaction of copper with copper 2 oxide. Now don't worry if we didn't quite get there. Lots more practice in just a second. So, writing ionic equations. Let's quickly review what I did there. The first thing I did was I wrote out the balanced equation. After that, I worked out the ionic formula only for the compounds which are ionic. Now our ionic compounds are acids, alkalis, salts, which would be metal and non-metal compounds, and any compound which contains a complex ion. Now those complex ions are things like your nitrate, nitrite, sulfate, hydroxide, those type of ions. You would then rewrite the equation using the ions, so including the ions instead of just the chemical formula. We're going to have more practice, just bear with me. So, aluminium reacts with oxygen to form aluminium oxide. So if we go up here, our word equation is aluminium plus oxygen gives aluminium oxide. AlO2 gives Al2O3. Balanced out, that's 4 aluminium plus 3 oxygen gives 2 Al2O3. And then we substitute in our ions, like so, and we have a full ionic equation. Now, what I would like you guys to do is use the rules here and the example that I have done for you here and try to write the balanced and ionic equations for magnesium and oxygen and iron 2 and oxygen. So what I'd like you to do is pause the video here, try writing those balanced equations and then restart the video and I'll work through them with you. Okay, let's see how you got on. So our first example then is going to be the reaction between magnesium and oxygen. So magnesium plus oxygen will react to give magnesium oxide. We already know that magnesium has the symbol, magnesium has the symbol Mg, oxygen as diatomic, so it's O2, and to work out the formula for magnesium oxide, we do Mg and O, which are our symbols. Our valencies are 2 for oxygen, and as magnesium is in group 2, it also has a valency of 2. If we swap those over, still 2 and 2, divide them down, 1, 1, our formula is MgO. Now remember, this is our chemical formula, we are not including any ions or charges at the moment. So I'm going to pop this in a box to keep it out of the way. Fabulous. Okay, Mg plus O2 gives MgO. This is, again, not balanced. So, 2 oxygens here, only 1 here. Put a 2 down. So I've balanced my oxygens now. I need to balance my magnesium, so I have 1 here and 2 here, which calls for 2 at the front. So we've balanced our equation, and this is where we have to add in our ions. Now, magnesium metal, not an ionic compound. Diatomic oxygen, not an ionic compound. Magnesium oxide, on the other hand, is an ionic compound. So here's what we do. We write out 2 Mg plus O2 gives us 2 Mg 2 plus O2 minus. And that is our ionic equation, and that is what you should have got when you tried that for yourself. Now, our next equation is iron 2 with oxygen. So, our word equation is iron plus oxygen gives iron 2 oxide. Iron has the symbol Fe, oxygen is O2, and iron oxide we will work out over here. Symbols are Fe and O. Iron has the 2 in Roman numerals, its valency is 2, oxygen's is 2, swap them over, 2 and 2, 1 to 1, Fe, O. So there is our balanced chemical equation. Sorry, there's our chemical equation is not balanced. We have 2 oxygens, 1 here, 2 here, so we've balanced our oxygens. To balance our irons, we go here, which is balanced equation. Now, as with our last example, the first half of our equation stays the same, and it is the second half that changes, because this is our ionic compound. Now, we still have a 2 at the front. Iron has a 2 plus charge, and oxygen has a 2 minus charge, and there is our balanced ionic equation. Again, if we're not happy with it, please don't worry. I hope that we are by now, but if not, we are going to have more practice. We'll stick with it. So, in case you couldn't read my writing, here are the typed out versions of those two examples there. And now we are going to go on to look at the reactions of metals with water. So, some metals, not all of them, will react with water. Most will react very slowly, but the metals which react most rapidly are the group 1, potassium, sodium, lithium, for example, and they are all stored under oil because of how rapidly they react with water. And group 2, from calcium down, also react quite quickly with water. Now their reaction, metal plus water gives metal hydroxide plus hydrogen. Now what Mrs. Leonard's done here is she's given the example of sodium hydroxide. Now sodium hydroxide can be written as, and I will write it here, underneath, if I can fit it in, NaOH. So what I've written here is the chemical formula for sodium hydroxide. Up here we have the ionic formula. So sodium is a positive metal ion, and our hydroxide ion is one of our complex ions. It's OH minus. So let's move on. Potassium reacts with water to produce potassium hydroxide and hydrogen. So metal plus water, metal hydroxide plus hydrogen. The word equation, potassium plus water, potassium hydroxide plus hydrogen. That is written as K plus H2O gives KOH plus H2. In this example, we have included our state symbols. So potassium at room temperature is a solid, water is a liquid, and when they react together, they produce potassium hydroxide in solution and hydrogen gas. The balanced equation, 2K plus 2H2O plus 2KOH plus H2. And our balanced ionic equation, all we have taken out here is our metal hydroxide, and we have given the ionic formula for that. So what I would like you to do is use this example and the ones we've already done before to write the balanced and ionic equations for the following reactions: calcium in water and sodium in water. So pause the video here, have a go, and then check back to make sure that you have done it properly. Okay, so calcium plus water react to give us calcium hydroxide plus water, written as a chemical equation. That's Ca plus H2O. It's liquid, calcium's a solid, and that gives us calcium hydroxide. I will work that out down here. So CaOH, valency 1. Oh, no it's not. Calcium's in group 2, so it's got a valency of 2. Hydroxide ion, valency of 1. We swap those over. They cannot be divided, so it's 2 and 1. So our chemical formula would be CaOH. Our ionic formula, which brings in charges, would be Ca2 plus OH minus. I'm going to leave this in its box down here. So calcium hydroxide is CaOH, and it's in solution, plus hydrogen gas. Okay, so let's take a minute. To balance our equation. So I've got 1 calcium on each side. I have 1 oxygen here. I have 2 hydrogens. I have 1 oxygen. And I have 3 hydrogens on this side. So what I'm going to do is we are going to put a 2 in front of here, which gives us 2 calciums. It gives us 4 hydrogens, and it gives us 2 oxygens on this side. So put a 2 here for a calcium. We then have to put a 2 here to give us 2 oxygens, but we now have our balanced hydrogens. So our balanced formula is 2 calcium, 2 water, 2 calcium hydroxide plus H2. Now, that is our balanced formula equation. If I get rid of the work in here. We are not quite done yet. Now that we have our balanced formula equation, we have to write it out as an ionic equation. So, as in the examples before, we're writing out our ionic equation. The first half of our equation stays the same. And it's the second half that changes. So it's 2 Ca2 plus OH minus plus H2 gas. That is the answer we all should have got. So let's move on to the next one, which was sodium plus water. So sodium plus water gives sodium hydroxide plus hydrogen. Please excuse my handwriting. So, sodium is Na, it's a solid. Water, H2O, it's a liquid. Sodium hydroxide, from a couple of slides ago, we already know is NaOH. That will be in solution. And then we have hydrogen gas. Is this balanced? No, it is not. So, NaHO, extend this line a bit, NaHO. So I've got 1, 2, 1, 1, 3, 1. So, I am going to put a 2 here, which takes my hydrogens to 4, also takes my sodiums to 2, my oxygen to 2. I'm going to balance my sodiums on this side by putting a 2 down here. I am then going to balance my water and my hydrogen, 2 here, so 4 and 2. So there is our balanced chemical equation. Now the ionic compound here is NaOH, so when we write this as a ionic equation, we do NaS plus 2 H2O liquid gives 2 Na plus OH minus, and that's in solution, plus H2 gas. If we were happy with that, let's move on. If not, go back and watch again, try and identify what we're not comfortable with, and then let myself or your chemistry teacher know. So, we've covered oxygen, we've covered water, we are now going to cover reactions of metals with acids. So metals above copper, anything that sits above copper in the electrochemical or reactivity series will react with acids. The reaction, which you must know, is metal plus acid gives our salt plus hydrogen. The salt comes from the metal and the negative ion in the acid. For example, in hydrochloric acid, the negative ion would be chloride. In nitric acid, the negative ion would be nitrate. And in sulfuric acid, the negative ion would be the sulfate ion. So, magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen. The equation for that, or the word equation, is magnesium plus hydrochloric acid gives magnesium chloride and hydrogen. We will substitute in our chemical symbols, Mg plus HCl, MgCl2 plus H2. Balanced out, looks a bit like this. Oh, looks like this. And then we will substitute in our ionic formula for our ionic compounds. Now, in this occasion, in this example, we're including acids, and acids are ionic compounds, so we've got to put their ionic formula in as well, which is why our hydrochloric acid, HCl, is included as H plus Cl minus. So, we are going to be doing the exact same thing that we did for the oxygen and water reactions, and this time we are going to do zinc 2 with nitric acid, and we are going to do sodium with sulfuric acid. So once again, pause the video, have a go at it yourself, and we'll see how you get on. So, our first example, we have zinc plus nitric acid gives us zinc nitrate and hydrogen. Now, our salt comes from the metal that is reacting, which is zinc, and the negative ion from our acid. And in nitric acid, as I said before, that is going to be our nitrate ion. So, down here, very quickly, I'm going to show you how to get the chemical formula for zinc nitrate. So zinc has a symbol Zn, and nitrate is NO3. The valency for zinc, we've been told it's zinc 2, so it's a valency of 2. Nitrate ion has a charge of 1 negative, its valency is 1. When we swap these over, 1, 2. We can't divide them by themselves at all. So our chemical formula is going to be zinc nitrate. So 1 zinc, 2 nitrate. I'm going to box this in just a second to keep it neat and tidy. So zinc plus nitric acid, which is HNO3. This was actually covered in the acids and bases topic, which was completed before the winter assessment. So if you don't remember your formula for your acids, flip back to your notes on that. It will be there, as we've just covered. zinc nitrate, which is ZnNO3 2 plus hydrogen. Now this will be solid, this will be aqueous solution, this will also be an aqueous solution, and hydrogen will be a gas. Is it balanced? No, it is not. So we're going to balance it. We've got zinc, we've got hydrogen, we've got nitrogen, we've got oxygen, zinc, hydrogen. Sorry, guys, I'm still getting used to my new graphics tablet, so you're just going to have to bear with me. So we've got 1 zinc, 1 hydrogen, 1 nitrogen, 3 oxygen. 1 zinc, 2 hydrogen, 2 nitrogen, 6 oxygen. Where did I get these numbers from? We have 2 NO3 according to this number outside the bracket, so everything inside multiplied by the number on the outside. 2 times 1 is 2, 2 times 3 is 6. To balance this, I'm going to come back over to my reactant side, put a 2 in front of my acid. It gives me 2 hydrogen, 2 nitrogen, 6 oxygen. So there we have our balanced chemical equation. Now what we also have to do is we have to get our balanced Ionic equation. Sorry, I'm just... Okay, so onto our balanced Ionic equation. We are going to replace the chemical equations, the chemical formula for our nitric acid with the Ionic formula. Remembering our state symbols, which Miss McPherson nearly forgot. And there we have our Ionic equations. Let's move on. Sodium plus sulfuric acid gives sodium sulfate plus hydrogen. Remember, the name of our salt comes from the metal that has been reacted and the negative ion in our acid, which in sulfuric acid is the sulfate ion. So we are going to go down here, we're going to do SVSDF to get the chemical formula for sodium sulfate. Sodium has a symbol Na, sulfate is SO4. The valency on sodium is 1 as it belongs to group 1. Now SO4 has a charge of 2 minus, it has a valency of 2. If we swap those over, they cannot be divided down at all. So our formula is Na2SO4. So we can then safely write out our chemical equation, which is Na solid plus H2SO4, which is an aqueous solution, to give Na2SO4, which is also an aqueous solution, and hydrogen gas. Okay, is it balanced? No, it is not. What must we do to balance it out? Well, it's quite an easy one. All we've got to do is we've got to put a 2 in front of the sodium. So we've got 2 here, 2 there, 2 hydrogen, 2 hydrogen, 4 oxygen, 4 oxygen, sulfur, sulfur. Pretty straightforward. So let's now do the Ionic formula. We have 2 Na plus our ionic formula for sulfuric acid and our ionic formula for sodium sulfate and our hydrogen gas. And there we go. Done. So, back to this reactivity series of metals. Metals react at different speeds with water, oxygen and acids. By watching or observing these reactions, we can organise the metals into how reactive they are compared to each other, an order of reactivity from least reactive to most reactive. Or in the case of in the table that we have, it goes from most reactive to least reactive. This reactivity series is shown here. So potassium is at the top, it's the most reactive, and gold's at the bottom, it's the least reactive. From potassium down to calcium, these metals will react with oxygen, acid and water. From magnesium down to lead, these metals will react with oxygen and acid. From copper to silver, the metals will react only with oxygen, and gold is completely unreactive, so it will not react at all. On your reactivity series on page 10 of your data booklet, you will have hydrogen included. Now, hydrogen sits in between lead and copper, and it's for you to compare how reactive these metals are compared to how reactive hydrogen is. So copper, silver and gold, they're all less reactive than hydrogen. Lead, iron, aluminium, magnesium, calcium, lithium, sodium, potassium are all more reactive than hydrogen. What it might be helpful for you to do is to pause the video now, get a hold of your data booklet and write on the data booklet on page 10 of your data booklet, which of the metals react with oxygen, acid and water, which react with just oxygen and acid, and which react with oxygen only, and then maybe put a wee star at gold to say it doesn't react at all. That takes us to the end of the lesson. So if you have not already done so, can you complete pages 52 and 53 of the exam practice workbook? Don't write in the books, they're going to be recycled for another group of 3rd and 4th years. So the exam practice workbook is the white CGP book. Do pages 52 and 53, and I will go over the answers to these at the beginning of the next session. What you also want to have done is you want to have completed pages 2 to 5 of your pupil book. I'll make sure there's a link to it handy. And there are also practice questions for the reactivity of metals. It would be good if you could have a go at them, see what you understand, what you don't understand, and if you have any questions, please feel free to email myself, email Mrs. Leonard, Mr. Shepherd. We're all very happy to help you out. Thanks for tuning in, guys. Have a lovely week.